Vision Convolution Kernels. In the world of artificial intelligence, convolution kernels, also known as filters, are important for processing visual data. They form the basis of convolutional neural networks, or CNNs. A convolution kernel is a matrix that slides over input data, such as an image, and produces an output. It is applied to small areas of the image to detect patterns, edges, and textures. Each filter in a convolutional neural network, or CNN, is designed to emphasize or minimize certain image features by applying specific weighted parameters to image regions. This is essential for performing operations such as blurring, sharpening, and edge detection. To optimize the network's ability to identify and interpret visual cues, filter weights are adjusted using methods such as backpropagation and gradient descent. This tool helps us demonstrate how convolutional kernels manipulate images in real time. Let's explore it. Here on the left, we have an input image. In the middle, we have a list of kernels and their associated matrix values. And on the right, we have the output image. Let's try to understand the concept of a kernel. A kernel is a small matrix used to apply image effects such as blur, sharpen, outline, or emboss. In this demo, all kernels are actually 3x3 matrices with associated values. These kernels are used in machine learning to extract the important features of an image. Here, we have a set of kernels that can be applied to the grayscale image on the left. To see how this works, let's first select the Sharpen kernel. The matrix values associated with this kernel are shown here as 0, -1, 0, -1, 5, -1, 0, -1, and 0. These X's signify multiplication. This matrix, or kernel matrix, slides or convolves around the input image, which is also a large matrix of pixel values. We take a block of pixels from the input image that is the same size as the kernel, in this case 3x3, starting at the top left and going through the entire image. We multiply each pixel value in the block matrix by the corresponding element in the kernel matrix and then take the sum. For example, if we take the first block, its pixel values are 22, 88, 113, and so on. We multiply these values by their corresponding kernel matrix values, such as 22 times 0, added to 88 times -1, added to 113 times 0, and so on. The total sum is 112. This is the gray level of the output pixel and is shown here. Now let's move the input pixel block on the image slightly to the right. That should be good. And we see that the block has pixel values of 88, 113, 99, and so on. These values are multiplied by their corresponding kernel matrix values and are added together to produce the output pixel value of 160. And this pixel is shown here. We compute these weighted sums for all 3x3 blocks of the input image to produce the complete output image with the Sharpen kernel applied. Now, if we select a different kernel, for example, blur, the matrix values for this kernel are 0.0625, 0.125, 0.0625, and so on. Once this kernel is applied to all blocks of the input image, we get this blurred output image as expected. This covers how this tool helps us organize images for efficient image recognition and training. Please feel free to play with the tool by selecting different kernels and analyzing their matrix operations.